Okay, so here is a example using implicit differentiation for a quote unquote practical application. And so what I did is I chose to do number 6 here, this boat problem. There are lots of classic problems like the shadow problem and so forth, but what I'm going to do is I'm just going to do this one here, and of course the examples will follow you. This one outlines the procedure pretty clearly. So, all right, so we have a pulley on the edge of a dock. We know that it's 6 feet above the water level, and the rope is pulling in this boat. And now we're going to assume that that's always going to be taut or tight, thus forming a right triangle the entire time in. Probably physically impossible to do, but yet that's the way we'll look at this, considering the waves going up and down and so forth. The rope is attached to the boat at water level, and the rope is being pulled in at a constant rate of 2 feet per second. Okay. So, in other words, this is changing relative to time. Okay. So, you can see what I have over here. I drew a right triangle. Should have put my little square in the corner here. But this side of the triangle is not changing. This is getting shorter. So obviously this leg also, which I designated as X, you can use any variable you want there, is also going to be changing. And so what we're saying is that X and Y are functions of a third variable, time t, which doesn't really even enter into the equation here, because where this relationship between X and Y comes in is just from the Pythagorean theorem, right? We just take this leg squared plus the other leg, which is 6 squared, and say that's equal to the hypotenuse squared. All right. So that gives us a relationship of X and Y. Okay. But remember, these two variables are changing with respect to a third variable, t. Okay, time. Now, once I get my equation in terms of X and Y, what I want to do is I want to differentiate that, because they're telling me that Y is changing at a rate of 2 feet per second. So I wrote over here, given the change in Y with respect to t, dy dt, the derivative of Y with respect to t, depending on which verbiage you want to use, is equal to -2. That's a constant rate. That rope is changing at 2 feet per what is it, second here. Yeah. And we want to find, they ask us to find the rate of the boat at which the boat is approaching the dock. Okay. So in other words, we want to find dx dt. And we want to find it at the instant, okay, where or when x is equal to 6, because that's when it's going to be 6 feet away from the dock. Okay. So it's going to give us a sense of how fast that boat is moving at that particular instant or point in time. So what I need to do is I just need to take this equation here. Just understanding, I'm going through all this so you understand what it is that we're trying to find here. Okay. So in essence, we're trying to find out how fast that boat is moving towards the dock at that particular instant when the rope is being shortened at 2 feet per second. Okay. And we're going to use implicit differentiation to do that. Okay, so this is a really simple equation in terms of finding its derivative with respect to t, because I just take the derivative of the three terms. So the derivative of x squared is just 2x, but again, using the chain rule, I have to write dx dt. This is just 0, so I'm not even going to write that. And then this is 2y, and then again, using the chain rule, dy dt. Again, keep in mind, what are we doing? We are actually, again, finding we want to solve for dx dt when x is 6. So all I need to do is I need to substitute in the values into this equation for x, y, and dy dt. Okay, in order to solve for dx dt. I just need to replace these variables here with the appropriate values. Well, they already gave me x, which is 6, and I just left the parentheses here just so you could see that that's all I'm doing is substituting in these three values, okay? So I'm going to put the 6 in for x, but what's the value for y? Well, all I need to do is go back to my original equation here and substitute in 6 for x and solve for y. And that's what I do down here. Okay, so again, use scroll and pause as necessary. So the 6 goes in for x. I simplify here. I got 36 plus 36 or 72. So y is the square root of 72. So that is what I pop in for y. And then dy dt, they gave me also, along with 6 equals x, that's the -2. So all I did here, I'm not going to go through the arithmetic here, but you just need to multiply all this out and then divide both sides by 12. And then when I simplify that on a calculator, I get dx dt to be equal to -2.828. And that is what I type in over here, okay? I noticed they say round to the nearest thousand, so I don't know what this was on the calculator, but apparently I did round it correctly because that is what they're looking for. So, be careful, when you enter these solutions here, be sure you read this. I know I've been preaching that along the way, but that's important to do that. Okay, you hate to miss a problem, have to do another one just because you didn't round correctly. And that's one of the problems with using MyMathLab. Okay, you got all this over here you do right, and then you round wrong, and you get you miss because you're one decimal place off, which is kind of frustrating, I would say. Okay. So that wraps up this particular week as far as the examples, or at least the way I have them worded on the announcements. And hope everything's going well for you. Be sure you can use the examples for some of the other related rate problems. But essentially, this is what you're going to be doing. You're going to get an equation. Sometimes you got to do a little work up here to get that equation, okay? You're going to use implicit differentiation to differentiate it, and you're going to be asked to find for one of these rates, and they'll give you the rest of the information either directly or indirectly. Remember, they directly gave me the -2 for dy dt. They directly gave me the x equals 6. I had to do a little bit of work to find the y over here. Okay, so that was indirectly given in lieu of the other information here. Okay, and then just once you differentiate, substitute the known values in, solve for the one that you're looking for, and there you go. All right, so that wraps it up, like I said, and we'll see you next unit.